All right, thank you for coming on time. So we're gonna get started, and I'm Holden. Dan introduced me on Monday, and today I will be giving the lecture. We're switching gears slightly. You've heard a lot about MRI physics. Today we're actually going to look at some of the math and signal processing. And you'll see that MRI is very amazing in that it combines all of these different STEM fields in order to gain an understanding of how to do something for biomedical applications. And I believe you all have handouts. So that matches my slides, and later on I'll be switching over to the document cam as well to go over some derivations. And feel free to ask questions at any time. Just raise your hand. So we'll get started. I guess you've seen something along the lines of this from Dan's slides already. It's showing you that in order to get from magnetic dipoles to actual images, there are many steps and many different concepts that we introduce along the way. You've seen many of these already, from going from B0 to B1 to different coils and gradients. On the other hand, you can see that this allows us to create magnetization, manipulate into the transverse plane, and eventually to generate signal. And there are some steps on the bottom that you haven't seen yet, but today we're going to talk about how a link is formed so you can go from the first few steps to the bottom few steps. And you'll learn more about each step later on in the class. Here, my job is to show you the math that's involved for making some of these leaps. So, a key thing to remember are gradients and what they do. And this goes back a couple of weeks. And just try to recall what gradients do. They establish, in this case, a linear magnetic field variation in the z direction. That allows you to change precession frequency at different spins, at different positions in space. And that's very important, as you'll see in the math and signal processing. This forms a bridge from the physical domain into a mathematical domain. The gradients actually allow us to impose some mathematical tools and analyses that have been well studied in different fields. And that gives rise to what we call the K-space signal and is directly involved in the formation of an image. We will start to introduce some of these concepts today, but you'll learn more over the course of the next few weeks. So let me start actually by going to the board, or the document cam in this case, and remind you about some of the physics that we'll be using to form our mathematical models. So let me switch over. And the derivation I'll start with is pretty short and concise. And actually it's a good way to work out some of the fundamental equations of MRI once you know the basics. Okay, we're in focus. All right, grab a pen. So we're starting from basics, some of the things you learned from the first week. And one of the things that is fundamental to MRI is the Larmor equation, as you'll remember. And this is very important because it establishes a link between your magnetic field and precession frequency. So let's look at the Larmor equation and how it can incorporate gradient encoding. Okay. And the Larmor equation, as you remember, is like this. there are only 3 variables. Actually, 2 variables, 1 constant for hydrogen. So gamma is fixed. What we manipulate is the magnetic field, and that gives rise to different precession frequencies. First, let me start out by spelling out what the magnetic field is composed of. And in actuality, it's a vector. And we all know that the main field has to be present. That's B0. And then, let me add on the gradients. So typically, we have gradients in all 3 directions. And here, I'm just looking at linear gradient fields. So this you've learned already. I'm just writing everything together. In addition to this, you've also learned that there might be other sources, such as off resonance. And remember that the magnetic field is in the z direction. Here I use I, j, and k as the unit vectors along x, y, and z. Since we're focusing more on what gradients and the main field do for us, let me ignore the other sources for now. So for now, let's just ignore. Ignore it for now. So we have a pretty simple equation that can be written in a more concise form. We still have B0, but now we can write the gradient field in a more general manner. So it's just saying that if the gradient field is a vector with components along x, y, z, then the net gradient field is just the dot product between G and your position R. It's very common, actually, to define R as a vector of your XYZ position. So far, there's nothing new, but you'll see that there's a lot we can gain from looking at these basic relationships. The first thing I want to define is omega 0. And this is very handy because we can eliminate it and simplify equations. If we have a field B0, then the main frequency is omega 0. This means we can look at what happens beyond omega 0. So let's look at what's left if we take out omega 0, which is actually often done, as you'll learn later on, to demodulate the signal you're getting, because omega 0 is at a very high frequency. And again, you can use the Larmor equation to write it like this. And you'll notice something very important right here. The frequency is actually a function of position. Okay, so far, pretty easy to follow, right? Let's keep that on the page for now and look at something that's related. So there we have how the frequency varies as a function of gradient strength and position. Now let's imagine that this is happening for a lot of spins throughout your volume. Each spin is actually at a different position. There are actually different things going on. Each spin has a different magnitude and phase due to these precession frequencies. We can write that out by considering each spin. Each spin has magnitude and phase at R. And this is very important. Here, it's, I guess, a simplified way to derive the MR signal. You'll have more rigorous ways later on. We can say that the MXY, or transverse magnetation, that we've generated actually varies according to spatial position and over time. And you've seen special cases of that already. Another thing to include is the phase. So right now, let me write in general terms. There's a phase component that's a function of position and varies over time. We know that phase is directly caused by frequency. So this phi can be written as just delta omega r times t. And we can bring that into the equation again. mxy So I'm explicitly writing out the phase term now, which is due to the off-resonance frequency, precession frequency multiplied by time evolution. And keep in mind that this is for each spin. Each spin at a different r has different magnitude and different phase. So what happens if we actually try to record signal from an entire object? We have an overall received signal from all of the spins. And let me make one simplification. Here, let's just assume we're looking at the first time point. And that it doesn't really change that much over time. We do know that there's T1, T2 decay that could be brought in to make this equation more complete. For now, I'm more focused on just the phase and how everything is coming together. Let me use S of t to denote the overall received signal. What happens is we actually look at an entire object. So the signal is an integration of everything in that object. And what is in that object? Well, a bunch of spins. Each spin has a different r, and we know what that looks like. mxy r, let's just use t equal to 0 right now. Okay. So based on our derivation, this is the type of signal we're getting from an MRI experiment. S of t is a summation of all the spins in an object, and each spin has magnitude, function of r, and phase, function of r. And the important thing to note here is that the phase is caused by precession frequency, which is also a function of r. Everything is integrated over space, dr. So this is actually math, which means there are mathematical tools that help us deal with this. In MRI, the big question is, how do we obtain mxy of r from S of t? Mxy of r is the thing you're looking at. S of t is what you're getting. So how do you find mxy? Well, today I'm going to show you the tools and analyses required to do this fundamental task. So does everyone have equations now? And we're going to come back to this equation. So from this point on, what I'm going to show you is not strictly limited to MRI. We have some general mathematical tools to use. Okay. So at the end of our derivation, this is what we have. The big question is, how do we form an image? And we need math. And in your book, the textbook, chapter 2, actually, it lists the math that is required for MRI, and I will go through some of the main ones. The first is complex numbers, which I'm sure most of you know, but we'll look at some of the important properties. Then there's convolution, which is a mathematical operation involving two functions. And this is very basic for a lot of signal processing approaches. Then we will look at Fourier transforms in 1 dimension and 2 dimensions, which is the key to working with a lot of the MRI math. If you already have taken courses in, let's say, signals or systems from other departments, some of this will seem familiar. you'll see that MRI is actually a beautiful example of how all this comes to life. And we will go on to look at linear time invariant systems, which is based on a lot of the math that allows us to characterize a operation or procedure involving different inputs of functions or signals. And furthermore, we'll look at sampling requirements because we use a lot of digital processing these days, and there needs to be a mechanism to go from analog to digital while we're forming these images. You think of images as discrete pixels, but a lot of the natural objects you're looking at are actually, let's say, continuous. So there is a bridge between these two realms. So any questions before I go on? No. Have any of you read chapter 2? Okay, it's in the book. I've tried to keep my notation similar to what's in the book, but some of these might be slightly different. There are actually in different fields slightly different conventions for naming the same things. Let me start with complex numbers. This is pretty standard. Everyone uses the same notation I equal to the square root of -1. You can see that in the complex realm, each number C has components of real and imaginary parts. You can draw this on a 2D plane, and you've already looked at some of this in MRI because we're dealing with complex signals. The thing to note is that the magnitude of a complex number is the L2 norm, or square root of the sum of a squared and b squared. And there is an angle involved in these complex numbers if you think of it as a vector in the 2D imaginary real plane. So we like to think of complex numbers as vectors. You can describe them this way in terms of the a and b components. Or, later on we'll look at a different way to look at complex numbers. Very important operation is the complex conjugate. You'll see this in a lot of transforms and mathematical equations. This just means that you are negating the imaginary component, or flipping it from one side of the real axis to the other side. It retains the same magnitude, but now the angle is actually negated. In terms of describing complex numbers, as I mentioned, there's another way, which is to look at magnitude and phase, which we do a lot in MRI. And the basis for this is actually Euler's formula, which states that if we have an exponential with a complex argument, we can expand it into real and imaginary components of cosine and sine. This allows us to look at complex numbers as being on a unit circle or circle of different radii. And using this approach, we have a very phenomenal equation of e to the I pi plus 1 is equal to 0. Under these conventions, we can write a complex number as the multiplication of its magnitude with its angle or phase, which is something we've been using a lot for MRI. You can see that the conjugate of this is merely flipping the angle. The magnitude stays fixed, as we've seen in the previous slides. Another important thing to note is that to compute the magnitude of a complex number, you're actually looking at the multiplication of a number with its own complex conjugate. And that corresponds to just squaring the magnitude of the complex number. Okay, that was quick review. I guess most of you know that already. Another important mathematical concept to introduce is convolution. Convolution is an operation that involves two functions. In this case, we have f of x and h of x. And this asterisk you see right here is actually the mathematical sign for convolution. And in some different texts, you'll have different notation. But generally, it's the asterisk. This means that we are performing an operation defined in terms of an integral going through all of space, where we have f of alpha multiplied by h of x minus alpha. You can see here that the argument you want to look at is x, which is right here. But you're manipulating the two functions over an entire axis of alpha, which is actually a dummy variable here. It commutes, which means that you can flip the role of f and h, so that you can write the integral with f of x minus alpha times h of x, the alpha. You can perform a substitution of variables to see that this is the case. And the integrals are very easy to write down. They have actually very far-reaching implications in signal processing. It's hard to understand at first, so I will go through some examples with you. And let's go back to the document cam. Let me work out some examples with you. One of the most basic examples to look at is if we have very simple versions of f and h. And here, let me look at two rectangle functions and see what the convolution result is. And the answer is already here. It's a triangle, but let's look at it visually to see what's going on. So for this part, I'm just going to write out the equations again and go through some diagrams of what happens when you're convolving two simple functions. You have 1D convolution. Oh, by the way, how many of you have seen convolution already? Okay, quite a few. Okay, I'll go quickly through the example. But for those of you who haven't seen this before, it's not very hard. And there's a reason that I've used f and h. This is actually convention. You'll see that f is used a lot of the times as your input function. H, as you'll see later on, has meanings of a kernel or, let's see, the transfer function. And here, let me just give the output a name so that it's easier to keep track of. So let's say the output is called G. You can see that in the output, the variable we're looking at is x, which corresponds to, of course, f of x and h of x. But in the integral, x is actually this variable that we're manipulating. And of course, you can see that since the integral can be exchanged, you can also write this as h of x log f of x. So let me go through a simple example of convolving two rectangles. And here we'll actually deal with the dummy variable alpha. So let me just write it like f of alpha. And we have a rectangle. It can be of any width, but here just assume that it's going from -1 to 1. On the other hand, we have h of x minus alpha to plot. We don't know what x is yet because it's a variable. We do know that the minus alpha entails flipping a function. Here, because the function is symmetric, flipping it gives us the same thing. So this is h of minus alpha. And here I'm assuming f and h are the same function, but generally they don't have to be. The output is g of x. So let's say we want to look at g of x at x equal to 0. What does that mean? Well, going back to our plots of f and h, we have to plug in x for where the integral wants it to be. So basically we have f of alpha and h of 0 minus alpha. And we look at the multiplication of these two functions. Since there's zero shift, actually the multiplication means everything under the rectangle is accounted for. And we have this point, which is at the x equal to 0 position. Now, as we keep calculating convolution, we keep shifting h to a different x minus alpha. So on top, we're keeping f in the same position. But now, let's say we want to compute g of x equal to 1. That means we're going to shift h. And now if you look at the overlap, we only get the area from this portion of the function. So if you look at g of x, this is the second data point in our g of x function. And you can work through this exercise on your own. In the end, what you'll get is actually something like this. So those two positions we calculated, x equal to 0 and 1, are merely just two data points in this final output. There are a couple of things to note here. First, we know that two rectangles convolved together gives us a triangle. And then there are a few more important details. One is that the output triangle is actually twice the width of the two rectangles, because if you look at how convolution is done, you go from one extreme end to the other extreme end. Basically, you're smearing out two functions. So this is actually going from -2 to 2. There are many important things we can do with convolution. All right, does everyone have that down? Let me go through a demo with you now, so it's easier to see animation on a computer to visualize things. Okay. This is a fun demo I found. Someone actually wrote this using tech. So it's the same example we just went through. We have two rectangles. In this case, they're called f and g. And you can see that f is fixed while g is flipped and moving around. On the bottom, you'll see the output, f convolved with g. So as you start, there's no overlap, so g doesn't have any value. Once you start getting an intersection, start integrating. You see that as you overlap more and more, the output gains more and more until you're fully overlapped and you're at the maximum value of the convolution. If you keep moving out, you'll see that the values, the output drop until you fully exit. So this is the extreme position. You see that both inputs have a width of -0.5 to +0.5. The output is -1 to 1. So visually and intuitively, this is what happens when you convolve two functions. And I believe you've already started using MATLAB. So MATLAB has a convolution function. And of course, if you wanted to, you can write your own, just to demonstrate and understand what's going on. Here I've just put together a very quick script to run convolution. And for one dimension, it's pretty easy to do these thought experiments. Later on, as we go into two dimensions, you can still visualize, but it's helpful now to have some code to back you up. Okay, so here I'm just creating two functions, two rectangles, and using the MATLAB function to get the g. So this is the example we just went through. If I have a rectangle, the output is a triangle. Pretty easy. Now that you have MATLAB, you can actually switch in any function you like. It will give you the result. MATLAB will be helpful later on as we go to the 2D case. Any questions so far? Nope. Too easy, huh? Let's keep going. Alright, next thing up is the Fourier transform. And this is Mr. Fourier. So the Fourier transform is used very widely in engineering. It's a way to analyze something from one domain and look at its representation in another. As Mr. Fourier was working on this early on, he was actually looking at heat transfer, looking at how heat propagates through different materials. It happens that it can be applied to almost any phenomenon that we experience. This is the definition of the Fourier transform, and you've probably seen it many times already if you've taken other classes. I'll point out some of the important components and properties of the Fourier transform. The first is we have an input function f of x as before. We put it into an integral and multiply it by another special function, which is an exponential. It's integrated over all of the input x, and that gives us something we call big F, and it has a different variable, kx, which is in the exponential. This is known as the Fourier transform of f of x. So there are a couple of things to keep in mind right here. We have an input f of x. We multiply it with a special function, and we get the output, which is in a different domain now. It went from the domain of x into kx. And you can write it either as, let's say, big F of kx or Fourier transform of f of x. So right now, it doesn't mean much to you, but it's an integral. You have functions and input, output. The nice thing about Fourier transforms is it can go the other way as well. So let's say we only have big F of kx. We can put it into another integral that looks very similar. The function we multiply it with is a bit different. Same arguments, but the sign is now positive. If you do this and integrate over the other variable, kx, you actually get f of x back. This is known as the inverse Fourier transform, written as ft minus 1 of f of kx. So we've learned another thing. That is, if we know f of kx, we can actually get f of x back. This will be very important later on. And the Fourier transform is very special because these functions that we multiply it with are known as complex exponentials. And they are very special in that they form an orthonormal basis. And I'll explain that a bit later. We've seen two domains based on this orthonormal basis, which has the nice property. So the complex exponentials form a set of orthonormal bases, but that's not the only one. We will only talk about this today. What it means is if you multiply one of these functions with its complex conjugate and integrate over all of x, it is equal to 1 if these two functions are the same. Or they cancel out if the two functions are different. That's very fascinating, because that means we can use this to decompose a lot of functions. Okay. So those are the definitions. And to help you understand, we have some examples in the next few slides. This is just the Fourier transform equation again, but let's look at it more closely. If we follow this forward Fourier transform, actually we're doing something called analysis. That is, we're analyzing what's in our input, f of x, into the many different components of big F, kx. One way to think of this is to give you an example. Here I have a specific example of an input f of x. It's a wavy signal that's periodic. It has oscillations on a high frequency scale and also slower variation. So, by the way, these examples are very simple. That's why it's easy to analyze them. But you can extend this later on. What we want to do with the Fourier transform is say, we have f of x. What is composition of f of x if we perform the Fourier transform? Well, without thinking about the Fourier transform, let's say, we can break f of x down into different components. You can see that there are distinct periodic oscillations in this function. There is a slow variation, which is kind of going along the envelope of this signal, and you can extract that. There's a second oscillation that's a bit slower than, a bit faster than this one, but still not the fastest. And you can see distinctly that there's a very fast varying component, which we can pull out like this. These components actually have names, and they are exactly these Fourier components that we're computing. You can see that this actually corresponds to f of 1. That is, f of x is made up of a certain underlying component of, let's say, frequency 1. It also has a component of, let's say, frequency 2.5, frequency 7. When you put all these together, you have f of x, and you can break it down into each one of these components. That means we're analyzing this signal. We can plot it this way, or there's actually a more concise way to plot this. We can just plot how much of each component we have in this kx space. You'll see that it has this much of, let's say, frequency component 1, and 5, and 7. They have different magnitudes. They also have different positions along this kx axis. And actually, I'm only showing one side. This will be a complex signal that has the other side. So, thinking about this example, let me go back to the equation again. When we do the Fourier transform, what we're doing is extracting the different components of the signal that correspond to different kx in the other domain. So when you see this in time, actually in frequency, it looks like this. If you have a pure tone, let's say a single sinusoid, you will only have one component in the spectrum for a k-space plot. Okay, so everyone kind of grasping the idea right here? We're able to represent a signal in another form. Now this example is simple, so it's very clean, only 3 components. Now we also looked at the inverse Fourier transform. So the intuition behind this is actually the opposite of what we just did. If we do this, actually we're synthesizing a signal. Imagine that we only have the components f of kx. We know how much of frequency 1 we have, 2.5, and 7 that we have. How do we recreate the signal? Well, that means first we have to have signal 1 at a certain amplitude, 2.5 at a certain amplitude, and 7 at a certain amplitude. These are the individual components that we understand from the Fourier space representation. When we perform this equation, it means that we're integrating all this. It means we're adding them all up. If we do that, well, here we are. We have f of x is equal to the sum of all these things. The magnitude is how much you have of that component. In this case, we have 3 discrete components, so the integral is actually just a sum. This means if we know a signal in its Fourier transform domain representation, we can exactly recreate it. And this will be important for many applications. Through this simple example, one thing you want to take away is that signals can have representations that look different in another domain. But if it's a good domain, then we can actually go the opposite way and get it back again. And you can see that here, actually, you need to represent this signal with a lot of data points. You need all of these data points just to describe this signal. Well, if you look at the other domain, you only need 3 points. So this is also important later on in some different image reconstruction tasks. All right? And the Fourier transform defines 2 domains, which I've alluded to before. It can be applied in many different situations. The most common situation is to think of a signal in time versus its spectrum, which is in frequency space. So you can think of this as an audio signal. And this is its spectrum. So we know that humans are sensitive, let's say, to a spectrum from 20 hertz to, let's say, 20K. If you analyze the signal, you can see what range of frequencies it has. And there might be components that we're not sensitive to. This Fourier space representation is also called the spectrum. For MRI, we also use the Fourier transform and deal with two domains. However, they're a bit different. Usually in MRI, we deal with space, which is represented by X. The other domain is a bit different. It's also a frequency, but it's spatial frequency. I'll show you some examples later, but typically we denote one by X, the other by Kx. And this has some history going back to physics when you're looking at diffraction and so on. And remember that the two domains are linked by the Fourier transform. It can go one direction and back again. And just for your reference, when we're using MRI, we're actually interested in images in the spatial domain. All right. So going forward, we have Fourier transforms. We need some better description of signals to understand how to model the world that we see. To do that, the mathematics community has defined a lot of very handy tools. The first one we've seen already in our convolution example. It's a rectangle. And more formally, it's defined like so, and there's actually notation involved because it's used so frequently. You can think of it as a very short blip that comes in and perturbs your system. You can also think of it as a window that you multiply with a signal just to retain a certain portion. All of that can be described by using a rectangle. Now, the Fourier transform of this rectangle is very important, and it has its own definition. It's known as the sinc function. If you go through the math of the Fourier transform, you'll see that a rectangle transforms into sine of pi kx divided by pi kx. And it's used so frequently that there's a special function named for it, the sinc function. And in signal processing, this comes up every day. Even, I think it's Broadcom, their company logo is based on the sinc. And an interesting property here is that if you integrate over all of sinc, you get 1, which is the same as if you look at the rectangle. And we'll look at some properties later on. Another important function is the delta function, which means that you're only interested in the value of something at one point. And actually, its amplitude goes on to infinity. If you take the Fourier transform of this special function, you actually get a constant throughout all frequencies in the Fourier domain. And the opposite is also true. If you have a constant all through space and you transform it, you will get a delta, okay, Fourier representation. Oh, I forgot to say. So here also, if you have a sinc in X space, its transform will be some type of rectangle in Fourier space. Now, what if we look at something slightly different? We're looking at a complex exponential, which is basically cosine plus I sine. Well, we're actually multiplying a constant with this complex exponential, and in Fourier space, it's actually shifting the delta. And there's a very important shift relationship. If the frequency right here is k0, then we're shifting this impulse by k0. And it's all math, actually. You can sit down and write through the equations. Now, sometimes we're only interested in a pure sinusoid, let's say cosine or sine. It turns out that because cosine is symmetric and real, its transformation is also symmetric. So you have two spikes, actually, each of half magnitude. If you look at sine, because it's anti-symmetric, it's a bit different. It's of imaginary amplitude and also anti-symmetric. Okay. Now this is even more interesting. What if we have a bunch of deltas, or those impulse functions in one domain? Well, if you take the Fourier transform, you actually get also a train of deltas. Here, because I've used a simple example, they look very similar. I've used unit spacing in x, so it also gives us unit spacing in kx. Actually, if you squeeze the impulses closer together here, in one space, they will be further apart in the other space. And we'll work on some examples when we go to sampling theorem. It also has a special notation, and it's known as a cone or Shah. I guess this is a Hebrew symbol. Okay. So we're seeing a lot of math. There are also some special functions that actually have the same type of structure in both domains. That's why they're often used, because it's a quick way to anticipate what happens in the other domain. If you look at a Gaussian, well, its transform is also a Gaussian. Again, if you have a thinner Gaussian here, the transform will be a fat Gaussian. And this is actually often used because it's easy to calculate. And based on those simple functions, you can actually describe or decompose what you're faced with, and then use some of these properties to extrapolate what the Fourier transform looks like. An important property is that the Fourier transform is linear, and it's defined like this. It's also defined by some similarity properties that I've alluded to. If you expand or contract in one domain, it's expanded or contracted in the opposite direction in Fourier space. Also, if you shift something, then you're creating a weighting by the complex exponential in the other domain. And we saw this when we shifted a delta function. Another important property is Parseval's theorem, which says that the energy is conserved as you go from one domain to the other. And of course, convolution. So we went through convolution early on. One of the most important aspects of convolution is that if you take the Fourier transform, you actually go from convolution to multiplication. And there are very important applications of this. One is that if you do a multiplication in one domain, effectively it's convolution in the other domain. And sometimes you want to do one or the other. Therefore, you can transform first to one domain or the other to take advantage of convolution or multiplication. And based on this property, actually, there's a whole, I guess, field of analysis that deals with system characterization based on linear time invariance. And I'll go into that right now. But before that, does anyone have questions? Nope? Okay. All right. So let's imagine we have an input function. It goes into some kind of system, which is acting upon f. And we can say that, let's say it's h of x. And the output is g. Now, in general, we don't know what to do if the signal is arbitrary. However, there are certain classes of signals where if you guarantee linearity of the system and time invariance of the system, then you can write this whole operation as a convolution. And as you see here, we can define the system output g of x as the convolution of f of x and h of x. This is very important because we can also look at these two functions, or three functions, in the Fourier domain. That is, we can look at multiplication of their spectra. And sometimes this is easier to process and visualize than going through convolution. Actually, sometimes you want to explicitly state the type of multiplication you want. That means the other way of looking at the system is looking at the Fourier transform, f of kx, giving rise to g of kx by multiplication with h of kx. And in this case, we know, or we refer to h of kx as the transfer function, and h of x as the impulse response. This is because if f of x is the delta function, then g is equal to h involved with delta and equal to h. So if the input is a delta, the output is its response, impulse response h. So let me walk you through an example. This is actually the same signal we saw earlier. So the three components now, I'm showing both sides of it on the spectrum. Let's say this signal represents some audio signal that humans want to evaluate. We know that beyond some range, humans can't hear anymore, so there's no use in using data to store that. What we can do is just retain the portion that we want to save, let's say, memory. That means we can explicitly just carve out the frequencies we want, in this case, two components, and discard the high-frequency component. In doing so, one way to define the system is to define this filter, this rectangle filter, h of kx, that directly multiplies the frequency response of f. In doing so, the output g is the components we want, the two low-frequency signals that we can hear. Right. And in doing so, we've very concisely described an operation by multiplication. If you actually design this in the other domain, it would be a convolution with a different looking function, which in this case, as you would imagine, would be some form of sync. Right? The problem with sync is it goes on forever in time. So it's very hard to do that operation in real time because you have to accrue so much data. Now, of course, getting the Fourier transform done also involves some processing. But once you're in this domain, you can quickly just multiply this rectangle with your input and get the output you want. So there are different ways to design this. This is actually a whole field of filter design. This will come in to be an important part later on when we talk about sampling, where we have to explicitly limit the amount of data we're sampling. Okay, it's right here. Okay, so far we've talked about math in the general sense of continuous functions and integrals. In the real world, we are limited by, let's say, memory or data acquisition speed. We only deal with discrete or digital signals. And here, when you talk about discrete and digital signals, there are actually two concepts. We take a continuous signal and go through analog-digital conversion to create a discrete series of numbers. There are two aspects. One is going from a continuous time signal to a discrete time signal. And this really depends on the A to B sampling rate. How often do we capture a data point from a continuously varying process? So if f of x was defined for every possible x, which particular indices are we capturing it for? We might go from, let's say, infinite number of samples to just the samples on time points that are even. Say we're going from this big signal to just the values at 0, 2, 4, 6, 8. That would be converting from a continuous time representation into a discrete time representation. The second aspect is looking at the values themselves. Generally, f of x can have any value associated with it. It can be rational, irrational. To record something on our disk or in memory, there needs to be some binary representation. And in doing that, we have limited quantization ability. So going from continuous to discrete values, we have to consider quantization resolution. That is, are you quantizing up to a certain range at a certain granularity? Well, that all depends on your system limitations. And in EE, there's a whole, host of classes and different, fields dealing with this. Today, we are mostly going to be talking about converting from continuous to discrete time representation. It is actually inferred that at some point, the values will have to be discretized. And on the scanner, it might be converting from a, let's say, real number into a 12-bit representation. We do lose some information there in either process, but we'll learn that there are theorems that guide us on how to do this, as to not lose any information. Okay. So let me run through the sampling theorem with you. And after this section, I think we'll take a break. So just keep focused for a bit longer. It's a lot of math, but very important math. Now going back to the signal we had, it's continuously varying. If we want to represent it, it means at every time point and every possible number between this range. You can imagine that's infinite and hard to deal with. The question is how to represent a continuous signal with only a limited set of numbers, limited in both time points as well as values. Well, let's look at the question of which points to sample first. Can we go from this representation to this representation and not lose any information? Well, they look quite different. And we'll learn that actually, if you sample at the right positions, you can actually recreate the signal. Okay. The other question is, how do we get it back? Well, it involves some type of filtering, actually. So many years ago, at the start of the mid-20th century, two important people, Nyquist and Shannon, actually worked on this problem. It was very important as people were making the leap from analog to discrete and digital. They posed a theorem in that if a function contains no frequencies higher than b hertz, it's completely determined by giving its values at a series of points spaced at least 1/2b seconds apart. So what does this mean? Well, another way to look at this statement is to look at how to recreate the signal. And this theorem can also be read as if a function f of t contains no frequencies higher than b hertz, it can be completely reconstructed from its values at a series of points spaced at least 1/2b seconds apart. And this is very important. So the sampling theorem tells us how finely we have to sample in order to recreate the signal. And you'll see that a couple of important parameters are at play. One is no frequencies higher than b hertz. So we have to characterize the signal first to know how much signal it has in, let's say, its spectrum up to a certain point. Second thing is to look at how finely we have to sample. If we know it has no frequencies higher than b hertz, then we can take every point with separation of 1/2b. So this is very closely linked. The other way to look at it is, if we're sampling at 1/2b, the best we can recreate is up to b hertz. So going both ways, and that's important. I guess it's best to look at an example. So right here, I have a function. It's f of x, and it's actually sig squared. You can go through the math. The transformation is a triangle. One way to understand it is two rectangles convolve to give a triangle. So what happens to the other domain? Well, the rectangle corresponds to a sink. So it would have two sinks multiplied together, sig squared. Well, the question now is, if we go from this continuous representation of f of x to its samples, what happens? Well, if you look at the math, go through what's happening. When you sample something, you're actually replicating its spectrum. When you go from continuous to discrete, you're replicating its spectrum at periodic intervals. And this is actually determined by how finely you sample. So let me go through some of this for you. Let's say we're sampling at a rate of ts. Every ts, we acquire one sample, and is actually also described by its frequency, 1/fs. We can write this as f of x multiplied by a bunch of deltas. So this Shaw function that we saw earlier. And because we're sampling at ts, it's written as x/ts. Every time x hits a multiple of ts, we have a delta function that multiplies with fx to grab its value. So that's how you write sampling math. Well, we've learned about Fourier transforms. So that tells us that if we do a multiplication here, it's a convolution over here. And because the transform of a train of deltas is a train of deltas, Actually, the convolution means we're replicating at different positions as determined by this train of deltas. We also know that if we're scaling by a certain parameter in X space, the scaling is of, well, if you scale down, then it expands in the other domain. So if we're at points of multiples of Ts, then here we're at points of multiples of Fs. And multiplication corresponds to convolution. So the separation is Fs equal to 1 over Ts. Now right now, it looks fine. We're not losing any information. It's just looking different. However, what happens if we go to a sparser sampling pattern? Say we're not sampling this finely, going a bit coarser. So we, let's say, skipped every other sample from the previous example. We're widening the sampling period. That means we're contracting these replicas in the other domain as Fs decreases. And again, right here, it doesn't seem too bad, right? We're just getting more replicas. Now, what can we do to recover the signal? Well, there's something known as interpolation, which can be described as a filtering operation. We know that this central copy of the spectrum is what we want. It came from the original signal. So if we can carve this out and throw everything away, we should get our signal back. Well, that's exactly true. If we can perform this very sharp filtering operation, it eliminates all the replicas, and in the other domain, we actually regain our signal. So it's very straightforward, huh? Well, not if you have limitations on your sampling period. Let's look at this example. So we're not able to sample that quickly, and we're going even sparser. You can see now that we're starting to have some problems. In the other domain, these replicas are squeezing together more tightly, and they're starting to exhibit overlap. That's not good, because it means we're disrupting the signal. And there's a specific term for that. It's called aliasing. And what does that mean? Well, if you look up the dictionary, aliasing has many literal meanings. One is masquerading. So it's mixing up of different frequencies. A low frequency pretending to be a high frequency. As you can see here, in the original replica, we have negative frequencies and positive frequencies. Here, the negative frequencies of the replica are mixing in the positive frequencies of the original copy. And that's not good, because once you do this, it's irreversible. And if you now do an interpolation or filtering, you cannot cleanly cut out the original copy of your spectrum. That means that when you're doing interpolation on these sparse samples, you do not recreate your signal. It's some aliased version, in that you have the same points, but the signal that goes through has limited frequency fidelity. You've lost some information because the high frequencies have been mixed up. You get this smoother, lower frequency looking reconstruction. That's not good. If you knew what range of frequencies you had, you could design your sampling beforehand. However, we don't always have that luxury. Sometimes we're guessing as to how finely we have to sample, how closely spaced the samples should be. That's where pre-processing comes in. So this is another example of aliasing. So this is a continuous signal that is adequately sampled. You see that samples are finely spaced as the sinusoid progresses. If you throw away a lot of that, then you have only these few points. And when you interpolate, it gets confused between this original high frequency signal and this lower frequency signal, which also goes through the same points. So this is aliasing as a result of undersampling. And there are actually a lot of real-world examples I could look up. There's a link that you might want to pull up later when you have time. But the basic idea is you've lost information. And in many cases, it's the loss of high-frequency information. It can also be loss of low frequency. It depends on how the aliasing occurs. All right. So how do we avoid having aliasing and loss of information? Let's go back to the Nyquist sampling theorem. If we have a spectrum, we should characterize its bandwidth or range of frequencies. Remember that if we characterize the bandwidth according to its maximum extent, we can denote that, let's say, by B. If our sampling frequency is greater than or equal to 2B, then the replicas will be spaced sufficiently apart and without overlap. That's what the Nyquist theorem was telling us all along. If you do that, then you can cleanly cut out or filter out the original portion to reconstruct your signal. And what happens in this case? Well, if you don't know the bandwidth to begin with, but you know your system can only sample up to frequency to 2B, you want to pre-process the input so that you don't have aliasing. So this might involve some loss of information, but at least not alias information. That is actually an error. What you would do is match a filter beforehand called an anti-alias filter to remove any information beyond your capable bandwidth before you sample. So you do this to any signal that comes through without even knowing its content. So you would chop this off before you sample, which gives you replicas. In this case, you have artificially imposed a bandwidth on your input signal, and that matches your system performance. Therefore, if you sample at f equal to 2b and cut out this central portion, you get the data back faithfully, but just in this band. So think about that a bit. You do lose some information, but you retain high fidelity for all the information that you've kept. This is a bit different from aliasing, where if you do not cut off, all the frequencies up to here would have been messed up. There's confusion up to this point. Okay. So let's take a 5-minute break and come back at 2:20. In the meantime, if you have any questions, feel free to come up. And after the break, we will do something fun and go from 1 dimension to 2 dimensions. Yes. Mm-hmm. Yeah, look at T in general later on. Here we're just having the first time.
Okay, so at the very initial one, we want to say that. Okay. Can you just explain this once again,
Oh, okay.
the same function?
Yeah. So if you take this rectangle and plug it in to the Fourier transform right here, and work with the map, you'll get actually a sum of a bunch of numbers. And it boils down to this equation. And this is what it looks like. The physical meaning is a bit harder.
Here it's clear like how I'm getting like this frequencies. Like here it is.
So actually, with a rectangle, you can think of it as having many frequencies. In order to create this sharp cutoff at the edge, you need very high frequencies. So you'll see the spectrum has actually values extending out infinitely in order to create this sharp edge. You can think of smoothly varying functions as having only low frequency constants. So like this. This is very smooth and slow, so it's very low frequency. Against this high frequency, very high in the Fourier transform. And then to create these edges, that's what you need.
So later on when you are talking here you mentioned something like 6 multiplied upon here.
Oh yeah. We have the original function f of x, which is a smooth function. In order to extract the points out of all these defined intervals, we have to multiply with this function, which is defined earlier, right here. So if you multiply something,
Train of delta.
yeah, train of delta. If you multiply it with the train of deltas, it picks out only values at the positions of the deltas. That's what we have here.
And how is it standard?
So this is, if you take the smooth function and go through the Fourier transform, it's a triangle. And you can calculate that directly or by looking at the example we had earlier. We know that two rectangles involved give a triangle.
Yes.
So that means here we have two sinks multiplied together because of the Fourier transform relationship. Just write that down. So we know that right.
Yes.
So we know this will be this Fourier transform. This is a 6 here.
Oh, so we are going opposite.
Fourier transform works both ways.
Actually, I never learned Fourier transform.
Oh, okay.
Chemistry.
I see. Well, you can find some textbooks to help you.
Okay.
Chapter 2 helps quite a bit.
Especially
Yeah, actually at the end of the lecture I will punch you through some references. All right, let's get started again. Any questions? Nope. For the next maybe half an hour, we're going to move from one dimension to 2 dimensions. And actually, all the math we've learned it applies to n dimensions. In MRI, we mostly work with 2 dimensions and 3 dimensions. So this will be very important to understand. in one dimension, it was very easy for us to think about time variation and frequency. Now, in two dimensions, it's harder because we don't have two dimensions of time. However, in MRI, we do deal with two dimensions of space, like x and y. That also has a Fourier transform, as we'll learn. So before we go into Fourier transforms, let's look at convolution. You've seen 1D convolution. This is the direct extension to 2D. You'll notice that all the equations look very familiar. We have, again, f and h convolved. And now you'll see that the arguments include both x and y. When you write out the integrals, you now have two dummy variables, alpha and beta. And they're flipped again, and you shift everything by x and y to get the values you want. So you can think about it for a minute. As we went through the 1D example, we had two rectangles that were shifting them on top of each other. Now, when you do 2D convolution, you can think of, let's say, two big squares in 2D space moving on top of each other. And I'll show you an example. Let's see. Okay. So for this example, I also have some MATLAB, but let's show some equations first. So I actually wrote this down already. So this first top half is actually just the equations in the slide you saw. So if you want to write something down, just look at the diagrams. Here I have two simple functions, f and h. You'll see that this is a square in 2D space. And I'm assuming again that h is the same as f, so that it's a square. And because a square is symmetric in x and y, when we flip x and flip y, it looks the same, as shown right here. Now let's look at the output. So g of xy is the convolution of f and h. We've learned from the 1D case that when you convolve two functions, the output is twice as wide. So I've pre-drawn an outer boundary that extends to twice the width of the input. And again, to get the results for different points in G, let's say 0, 0, we would shift h by that amount and look at the overlap between f and h. In this case, to calculate x equal to 0 and y equal to 0, right here, the two functions actually overlap entirely. So that will give us the maximum value in this convolution. Next, if we want to calculate another point, say x equal to 1, y equal to 1, we will shift h so that we have h of 1 minus alpha and 1 minus beta. In this case, the overlap is now smaller. Only this small quadrant gives any contribution to the convolution output. So does anyone want to guess what the output looks like? So I thought I heard something. Pyramid. So it will be very similar to a pyramid. Not exactly. But to find out, let's go to MATLAB. You all have this? Okay. So this is, again, some simple code I put together. I've defined two functions. Both are in 2D space. These are two squares. And then I'm calculating the convolution using the conv2 function in MATLAB. And to plot these functions, there are a couple different ways. All right, go slowly. Okay, so this is our input. This is f. It's a square. And in this case, h is the same as f. When we convolve the two, this is what we get. So it's very similar to a pyramid. You can see that it's very bright in the center, has some ridge lines, and it dissipates towards the edges. If you compare the width of the two, you can see that the convolution result is twice as wide as the input. And this is a surface plot of the output G. You can see here that it's in grayscale, but if you visualize it as a 3D representation, this is what you get. You see that it's highest in the middle when the two functions overlap, and it tapers off as you go outwards. So you can also play around and input different functions. I can make this simple script available on the web page. Okay, so moving on, we also have the Fourier transform in 2 dimensions. The mathematical notation is very similar. The only thing we've added is an extra variable. Now it's f of x and y. The exponential here has both kx and ky, and the output is a function of both kx and ky. We have this forward Fourier transform as well as the inverse Fourier transform. Everything's the same, and the main difference is just that we've introduced y. And now our bases are in 2 dimensions. So for the 1-dimension example of Fourier transform, we looked at sinusoids in time. It was easy to visualize what these complex exponentials meant. For the 2D Fourier transform, it's a similar concept, but slightly different. So in this case, it's good to think about spatial frequency instead of temporal frequency. Temporal frequency means something is varying as time progresses. Spatial frequency means something's varying as you move in space. And going back to Euler's formula, we can see that this complex exponential is decomposed again into sinusoids, but they have slightly different appearance. You have, in general, a real and an imaginary part, dictated again by cosine and sine, but as a function of 2 variables. So to see what that means, I plotted a series of 2D complex exponentials for you to look at. This first example is actually just 1-dimensional, or it could be 1-dimensional. So this is our good old cosine and just x. Here I've eliminated y. If you look at this function along just 1 dimension, it's actually the same as a 1-dimensional cosine, right? As you go around and move along this direction, you see a cosine. Okay. It can do the same in the other direction, just variations along y. But note that I've been plotting this in 2 ways. You can look at it this way as a 2D top-down, or as a 3-dimensional object. You can again vary the frequency in each direction. This is purely along y. But it gets interesting now if you look at both directions. In general, we can manipulate both kx and ky to give us different frequencies along x and y. That means if you move only along x, you'll see one frequency. If you move along y, you'll see the other frequency. In this case, they're both 1. So if you move from top to down, you'll see 1 period. Move right to left, you'll see 1 period. Actually, when you put this together, you have a cosine that's varying in both directions. And you can keep increasing the frequency for one or both of the dimensions. In this case, ky moves faster. Now to characterize this, we can actually look at an expression that decomposes this spatial frequency into its direction and period. You can see that the direction of the sinusoid is determined by the ratio between ky and kx. And the frequency at which you see the peaks and valleys is dictated by the sum of both. So these are actually very familiar from our discussion of the complex numbers. One way to visualize spatial frequency is to think about, let's say, what happens when you're hiking. So when we talk about spatial frequency, it's something that's varying in space. And you can see that as, let's say, mountains and ridges in space. So in this case, you would see like variations that go slowly in this direction, while they go very fast in this direction. And sometimes they have higher peaks, sometimes they have lower peaks. And interestingly enough, if you take the Fourier transform of this representation, you actually have a bunch of 2D spatial frequencies. And something you can do, or actually it might be an exercise, you can download this image and try to get the Fourier transform of it. The 2D Fourier transform, again, has all the properties of the 1D Fourier transform. We again have linearity. We have the scaling property, and also the shift property. But all of these are now extended to 2 dimensions. We again have conservation of energy, so that the sum of the squares in one domain is the same as sum of squares in the other domain. And again, our good friend convolution that we just saw also has an associated Fourier transform property, in that if you convolve 2 2D functions, it's the multiplication of their spectra in 2D Fourier space. All right, so with all that math in mind, let's go back to the signal equation we saw at the beginning of class. Okay, so this is where we ended at the start of class. We went through the Larmor equation, we added in gradient encoding, and this is the equation that we got. Now let me work on that equation for a bit. Okay, so let me just write the signal equation again. And you might have this already in your notes. Let me simplify this a bit. So let's say we have an object. For the sake of simplifying things, let's just consider one slice for now. And you will learn next week how this is done. Let's consider one slice with a certain thickness, AZ. That helps us to simplify this equation because we can now look at only the x and y dimensions of the object. So basically, I've reduced R from x, y, z to just x and y. And you'll see that I'm making this simplification so that we can make use of the math we just learned. And let me further simplify it so that we don't carry around the mxy that much. Okay, so this is what we have after the simplification. It's an integral of a 2D function, m of xy, which we're interested in, multiplied with the complex exponential that we learned a lot about. Now, one key point is to remember what delta omega xy is. And this is the Larmor equation that we looked at the start of class. Now, with this in mind, we can substitute and write out the signal equation again. So I'm just plugging in and expanding the terms contribute to the precession frequency. And let me do something that doesn't seem obvious right now, but will become clear in 1 minute. Let me reorganize the variables a bit. Okay. So I'm introducing the factor 2 pi, and then I'm grouping gamma with the g and gx, gy terms together. So some of you might know where this is going, but let me make some definitions. Let's define this variable, kx of t. And it's kind of a giveaway since we've learned about kx. Well, okay. And this is actually known as k-space. With these definitions, we can actually substitute and further simplify the signal equation. Okay, I'll give you a minute, just write that down. Does anyone know what this looks like? Yes, it's a Fourier transform. So, write it like this. Okay, so that's why we went through all that math. Because MRI actually fundamentally is a Fourier transform relationship. And it's very beautiful. You can see that right here. This is what we want to know. This is what we can control and manipulate. This is what we actually receive. So what is MXY? Well, we know that if this is a Fourier transform, as long as we have enough measurements, we can actually invert this relationship and recreate or reconstruct M of xy. Let me switch back to the laptop. And here we have the same equation as the last line in the derivation. By defining these special variables, kx and ky, we've actually massaged the MRI signal equation a bit, and that revealed a Fourier transform relationship. So everything that we learned in class today, all of the relationships, all of the properties can be used here for MRI. And if we want to figure out the underlying big M of xy, which is our object of interest, we can take a Fourier transform of our measurements. This means we're going from this defined Fourier space, or K-space, back into the spatial domain, xy space. And this process is, I guess, the basic form of image reconstruction for MRI. And you'll learn more about that. Fundamentally, it means we're recording data in one domain, going back to the other domain to form an image. And I always love giving this lecture because this is exactly what they awarded the 2003 Nobel Prize for. And this was given for discoveries concerning magnetic resonance imaging to Drs. Lauterbur and Sir Peter Mansfield, because they realized what a gradient does. And this was not actually widespread knowledge until this point in time. There have been different people who looked at the properties of gradients. Really, it was Lauterbur and Mansfield who linked gradient encoding to the formation of images. Namely, if you control the precession frequency as a function of space, you can form the spectrum and derive information regarding the spatial representation of the object. So after this class, actually, you have Nobel grade knowledge. So very exciting. 30 years ago, this was, I guess, cutting edge. Now it's accessible to everyone. And it's very amazing in that it, I guess, takes advantage of mathematics that was very much theoretical, and it has this very natural manifestation for MRI. And it's actually used as a prime example when they teach Fourier transforms now, to show the power and the prevalence of spectral analysis. So I'll show you some previews of what's ahead. Now that we understand the relationship between images and the signal we record, we can be very systematic. We can say that this is the image we want, M of xy, and understand this is the data we record, M of kx, ky. At first glance, this is just a bunch of numbers. It's not an image, but we know now from the math that it is equivalent. If we look at each point in this 2D spectrum, if you will, each point represents a spatial frequency. As you go out further in K-space, you get higher frequencies. If you go in different directions, you have spatial frequencies in different directions. As shown in that map earlier, if you put all these spatial frequencies together, you have peaks and ridges, valleys. And that actually corresponds to images. So if you take the Fourier transform of this collection of numbers, you actually get the image. And of course, in MRI, it's a bit more complicated. You actually have complex data, which gives you extra information. So this was a quick, I guess, preview of what's to come. And a lot of the steps I touched on today, you'll learn in more detail in the next few weeks. The first is signal localization. I've made an assumption that we can control the acquisition to only target certain dimensions. And there are actually physics behind that and hardware developments. I've given you a very quick glance at the MRI signal equation, but it's actually more involved than that. We assumed that we already had the magnitude and phase of each spin, and we could just sum everything together. In the real world, you actually have to induce and collect those signals, and later on Dan will talk about how this is actually done physically. I've introduced K-space, but putting K-space and sampling together means that your acquisition has to have certain properties in place. And you'll learn more about that when K-space sampling is introduced in detail. We've covered the basics of image reconstruction, which is a Fourier transform. And based on this mathematical formalism, there are a lot of new technologies you can incorporate. And because it's math, there are a lot of mathematical principles you can take advantage of, like sampling only half of K-space or skipping every other sample. And in the end, when you image, there are a lot of quality and practical issues that might seem random at first. But actually, if you go back to the physics and math, it can be well simulated, even predicted. And that is actually a very, I guess, beautiful aspect of MRI, in that you can actually fully simulate a lot of things you see. And from your observations, you can actually infer what happened at the basic level. So that's not always possible. with other modalities. And the message today is we covered math and signal processing. Why do we do that? Well, MRI is actually built on that. And I encourage you to take other classes if you find this very interesting, because the methodologies employed, let's say, in digital filtering for EE is actually applicable here for many different aspects of MRI, like RF pulse design and so on. If you're interested in more of the math and you don't want to go to the class, there are further reading materials that you can consult. One is Chapter 2 in our textbook, as well as some of these other often used textbooks in MRI and signal processing. So let me know if you need a specific citation or reference for any of these. And I'm around. If you have any questions, please email me or check out our webpage. And Dan will probably advertise for us, but after this class, there's another class that I teach with Dr. Kyung-sung, and we actually expand upon a lot of these principles. And we do more MATLAB. That will be very fun for you. So thank you today, and just let me know if you have any questions. Thanks.
Thanks, Holden.